Hi guys, Miss Francis. So now I'd like to discuss our first group of macromolecules, carbohydrates. Carbs are organic molecules and they are made from the elements carbon, hydrogen, and oxygen, where there's a 2-to-1 ratio between hydrogen and oxygen. Now the simplest carbs, glucose for example, is a monosaccharide, mono meaning one. And we can tell a carb by its shape, where carbs are going to have a ring shape. So this monosaccharide, this simple sugar, is going to have one ring. A disaccharide is a double sugar. It's going to have two rings. So it's going to consist of two monosaccharides joined by that process we talked about yesterday, dehydration synthesis. Polysaccharides are polymers of monosaccharides, and they are going to consist of many rings. So let's talk a little bit more about sugars, the smallest carbohydrates, and they serve as a source of energy. Monosaccharides, particularly glucose, are a major fuel for cellular work. And as I mentioned before, you can recognize a monosaccharide because it has a ring shape. These small sugars, these monosaccharides, generally have a molecular formula that's some multiple of CH2O. So for example, glucose has the formula C6H12O6. And most names for sugars, most names for carbohydrates end in OSE, such as glucose, galactose, and fructose, which are three types of monosaccharides. So how are these monosaccharides classified? Well, they can be classified by the number of carbons in the backbone. So glucose and other 6 carbon sugars are considered hexoses. So it will be, you know how the formula for glucose is C6H12O6. That means there are 6 carbon sugars in the backbone. 5 carbon backbones are considered pentoses. That would be like a ribose or a deoxyribose. 3 carbon sugars are your trioses. So let's look at examples of triose sugars, pentose sugars, and hexose sugars. So for example, glyceraldehyde, or sometimes shortened as G3, is a triose sugar. And you see how in the molecular formula there are 3 carbon atoms. We could look over here at the pentose sugars. An example of a pentose sugar, as I said, is ribose, where pentose sugars are going to have 5 carbons. Lastly, if we look at hexose sugars, those that have 6 carbons, popular 6 carbon sugars are glucose and galactose. Glucose, galactose, and fructose, if we notice them, they all have the same molecular formula. They all have 6 carbons, 12 hydrogens, and 6 oxygens. Therefore, they are considered isomers. Remember that vocabulary word that we learned yesterday. Here we can draw the molecular structure of a glucose molecule. Remember, glucose is going to have one ring because it's a monosaccharide. You put an oxygen in the corner, and remember, at each one of these vortexes, you're going to have a carbon, and then your 6th carbon is up here. All right. This video by Stephanie Castle is an excellent video that shows you step by step how to draw a glucose molecule. So if carbohydrates have multiple hydroxyl groups, remember that's what the OH stands for. OH is a hydroxyl group. Will they be hydrophilic or hydrophobic? Well, we talked about this earlier. Within that OH, there is a polar covalent bond. That means that it is hydrophilic. Because it is hydrophilic, they will dissolve in water. So they're going to aid in the solubility of any organic compound, in this case carbohydrates, that has a hydroxyl group. Now we talked about the reaction that joins monomers. We already went through this, but now we'll take official notes. Includes the hydroxyl group. So when we form our disaccharides from our monosaccharides, we do the process of dehydration synthesis, which involves the hydroxyl group. So as far as the hydroxyl group, it's made up of the elements oxygen and hydrogen. Its structure is OH, where there is a polar covalent bond between the OH, and alcohols are commonly compounds that contain this group. So why is this significant? Like we said, it improves the solubility of those organic molecules. And we already stated this, that organic compounds with hydroxyl groups are alcohols. And typically their names end in OL. So you've got glycerol, you've got ethanol. Now let's talk about disaccharides. So when I join two monosaccharides with that process of dehydration synthesis, I form a disaccharide where a glycosidic link is formed between those two monosaccharides to join them. So instead of like a covalent bond, it's a glycosidic linkage between them. So the three disaccharides that we need to be familiar with are maltose, sucrose, and lactose. So let me tell you what those three sugars are. So maltose is a malt sugar, and it is formed by joining two glucose molecules. Sucrose is table sugar, and sucrose is a naturally occurring sugar in plants like cane sugar or beet sugar. And that is formed by joining glucose and fructose. Lactose or milk sugar is formed by the joining of glucose and galactose. Some people are lactose intolerant, right? So they don't have the enzyme to digest lactose. So let's take a look closer at the formation of maltose using dehydration synthesis. So we've got glucose, right? Which is C6H12O6, C6H12O6. And we're adding another glucose, C6H12O6, right? So glucose and glucose is going to give me maltose. Well, when I add them together, wouldn't that be C12H24O12? I don't know. What do you think? Use what you know to figure out the molecular formula for maltose. Exactly. I forgot to take out the water. So if I take out the water minus H2O, I'm left with C12H22O11. And I still have that H to O 2-to-1 ratio. Right? So if I wanted to fill in the formula, I would say C12H22O11. Now let's figure out the formula for sucrose. Oops. So sucrose is glucose and fructose. Glucose is C6H12O6. So is fructose, C6H12O6. So again, you would think that we would get C12H24O12, but remember, we need to take out H2O. So that leaves us with the molecular formula for sucrose as C12H22O11. Now let's take a look back at our diagrams. Right, so here we've got glucose and glucose. We're removing a water by taking a hydroxyl group from one of those glucose and a hydrogen from a hydroxyl group of the other glucose, and then we're forming a glycosidic link or a glycosidic linkage to form maltose. And this process is known as dehydration synthesis. Again, the same to form sucrose, right? We're taking glucose, we're removing a hydroxyl group from one and a hydrogen from the hydroxyl group of fructose to give us water, which will then join together to form sucrose via a glycosidic linkage, where the formula for sucrose and the formula for maltose are the same. So they are isomers. Let's look at the dehydration synthesis or condensation of lactose. So we've got galactose plus glucose. What did they not represent over here? There's a water coming out, but they showed it to us over here. And what type of link is going to be formed here? That's right, a glycosidic linkage. Here are some videos and animations from Stephanie Castle that will really help explain how monosaccharides are joined via condensation reactions. When you get a chance, let's go through the review. So maltose is, this should say A, B, C. Maltose is glucose and glucose. Sucrose is glucose and fructose. Lactose is glucose and galactose. Now let's take a look at their descriptions as far as the functions of each of those sugars go, each of those disaccharides. So maltose, again, well, what does maltose do? You tell me. It's malt sugar. All right. Sucrose transports energy in the phloem of plants, right? It's in that cane sugar and that beet sugar. And which of these have the molecular formula C12H22O11? All of them. They are all isomers of one another. They're disaccharides that have the same chemical formula, but they're going to have a different structure, a different shape, and therefore a different function. And that ends our discussion of monosaccharides and disaccharides. Tomorrow, we will talk about polysaccharides.